In this video, you're going to be getting the ultimate kinematics solving guide. We're going to hit up 7 problems with a variety of different calculations in order for you to build up the concepts, the calculation strategies, and just the overall approach and mindset necessary to be successful in these kinds of problems. We're going to start off with some more simplistic problems that are at constant velocity, move up to ones that have accelerated motion, free fall, and then two-dimensional projectile motion. In the box here, we have a summary of the different questions we're going to be looking at. We're going to start with number 1, our blue question, and work our way down all the way to number 7 to a fairly advanced projectile problem. All right, so let's get started with the first one. We have a constant velocity problem. All we need for a constant velocity problem is our formula delta x over t equals v. And our delta x is displacement. Delta x means the change in x position. Time is just how long it takes for whatever to happen. And then velocity is how fast the object is moving with direction shown with a positive or negative. Now we have a car that drives across a distance of 5,000 meters. It's going 25 meters per second, and we're going to determine the time it takes for this trip. So first step in all of our problems is definitely labeling your known variables. So our delta x, which is the same as our distance, it's how much the position changes, is 5,000 meters. We have a velocity of 25 meters per second, and then we're going to determine the time. All right, for this one, we already labeled all of our known variables. We labeled the variable that we're looking for with a little question mark next to it. And then you go ahead and pick the formula that matches up with it. Since we're working on a constant velocity problem, we only really have one option, delta x over t equals v. So then we're going to go ahead and put that right into the formula, substitute in our known variables. And then after we do that, then we're ready to do a little bit of algebra and problem solving. So for this one, you could go about it one of 2 ways. I'll show you the more formal route, and I'll show you kind of like the quick little easy way to solve this problem. So we have t in our denominator here. If we want to solve for t, we definitely want it out of there. So we're going to go ahead and multiply both sides by t in order to get it out of the denominator. And then from there, what we're going to do is, now that we have 25 times t equals 5,000, do the opposite operation to isolate our t, and then divide both sides by 25. So 5,000 meters divided by 25 seconds gives us our final solution, and then the time comes out to 200 seconds. Okay, now the other thing you could possibly do is basically the same thing, but say for example you have the 5,000 on this side, you have 25, and then the t on the bottom here. Basically all you're actually doing is you're cross multiplying these two. So the way I think about it in my head, now that I've done many of these, is doing a little bit of cross multiplying. And then the 25 is going to switch places with the t. In the end, both operations are pretty much the same thing. You take 5,000 divided by 25 in the end. So whichever one clicks with you or is more comfortable for you to problem solve with, I would take that method. All right, that completes our first question. Let's go ahead and move to our second question, the red one. Now we're going to start this classic kinematics problem where we have 2 cars approaching each other. When you have stuff that's a little bit more complex, you definitely want to draw a diagram to assist you in visualizing what's happening in the problem and to make sure you have all of your variables in line with the correct sign. So we have a car that is going 2 meters per second. Oops, that's not a 2. A car that's going 2 meters per second, and then from 550 centimeters away, we have a car that approaches it moving 3 meters per second. So because it's going in the exact opposite direction, we're going to call that -3 meters per second. And we're going to find out how long it takes for these cars to collide and where do they meet. So we're looking for a time and a position where this occurs. All right, so we're still using delta x over t equals v. We're going to rearrange that a bit. So delta x is final minus initial position. And what we can do is we actually want to rearrange this problem and set it equal to xf, the final position. So the t gets multiplied on each side, so then that goes to the right side next to the t, and then after that one is scooted over, then we're going to add the initial position to both sides, which is going to cancel on the left side and then send it to the right side. Okay, the reason why we do that is because if we're talking about two cars colliding, that means that they have the same final position, which means that their vt plus xi for each one of these is equal to one another. So for this car, its velocity is 2 meters per second. We don't know how long that's going to take. And it's starting from, we'll call this position 0, and we'll call this position over here 550. We also want to make sure we're in the standard units, so we're going to take 550, divide it by 100, and then we're going to call that 5.5 meters. Okay, so this one's starting position is at 0, and this equals xf. Okay, but the xf for this one equals the same as the xf of the other one, and xf equals vt plus xi. So the velocity for the other one is -3 times t, and this one does have a starting position away from 0, which we're calling 5.5 meters. Okay, and from there, we're going to do a little bit of math. We have 2t, and then we don't really care about the 0, equals -3t plus 5.5. We're going to add 3t to both sides, and then we have 5t equals 5.5. And then we're going to divide both sides by 5. And then that's going to get us 1.1 seconds. All right, so key parts of this problem was, number one, we for sure wanted to make sure we had this negative sign for the 3 meters per second to show us going the other direction. We also wanted to make a little conversion over here, make sure everything is in meters, seconds, and meters per second, and then we could go ahead and set the VT plus XI of each car equal to each other because they have the same exact final position, because if they're colliding and meeting, then their final position has to be the same. Now we got the T, now we just want the final position. Now what you can do for the final position is you could use either one of the formulas to find it. One of your formulas was 2t plus 0, the other one was -3t plus 5.5. Okay, 2t plus 0 is going to be the easier one to use. I mean, they're both not very difficult, but 2 times 1.1, and then I'll just put the plus 0 anyways, is going to give us our final position, which would mean our final position is 2.2 meters. Okay, again, if I wanted to, I could have plugged that into the other formula. What that would have looked like is -3 times 1.1 seconds plus 5.5, okay, which still equals 2.2 because they have the same final position. All right, that does it for our second problem. Let's go ahead and move into some accelerated motion with question number 3. All right, so we're on to our first accelerated motion problem, and now we're going to have to introduce some new formulas. So we have the acceleration is the change in velocity, which is VF minus VI, final minus initial velocity over time. We also have the displacement equals the initial velocity times time plus 1/2 acceleration times time squared. And then our final formula that we're going to use is VF squared equals VI squared plus 2A delta X. Okay, so depending on what we're solving for, now we definitely have some more options, which is kind of a good thing and a bad thing. Good because there's different ways we can solve a problem, and then bad because we have more things to pick from, which makes our job a little bit more difficult. All right, let's get into our first accelerated motion problem. We have a car that comes to a stop that's going 14 meters per second. It comes to a stop after 3 seconds of braking. How long does it take and how far does it travel? All right, so it looks like it's going 14 meters per second in the beginning, and it comes to a stop, which is implying that the final velocity is 0. Okay, you want to make sure that if it says starts from rest or comes to a stop, we know we can use 0 meters per second somewhere, and then we have a time of 3 seconds, and then, oh, actually, wait a second. The problem is actually incorrectly written. It's not how long does it take, because we already have that. We're looking for the acceleration and then also how far it travels. Okay, so we have the time, and we're going to find the acceleration, and we're also going to find the delta x. Now, when you have a problem like this, now that you have accelerated motion formulas that clearly have a lot more variables, you need 3 known variables to solve for everything. Okay, for the constant velocity formula, because it was only delta x over t equals v, you only needed 2 things to solve for the third one. For all of our green formulas, you're going to need 3. Okay, so if I'm looking for my acceleration, all 3 of my formulas have an a in them, so all of them could potentially solve for a, so we want to find the one where you have everything except a. So if I look through my first problem, do I have VF? Yes. Do I have VI? Yes. And do I have time? Yes. Okay, so that actually worked out. I'm going to go ahead and use my first formula and say that acceleration equals VF minus VI over t. Okay, which basically just comes out to negative 14 over 3. No algebra necessary. And then we get an acceleration of negative 4 we'll go ahead and round that off, 67 meters per second squared. All right, we have the acceleration. It is negative because the thing is moving in the positive direction and it's braking. So you're basically adding negative 4.67 meters per second per every second that it moves, or subtracting, either way. So you're knocking off that amount of velocity per second until it hits 0. All right, moving on to the next part. We're going to find out how far it moves, so we're going to have to use a delta x formula. If I take a look at this one over here with the VF squared, I do have the VF, I do have a VI, and I do have an a, so I can find the delta x that way. If I used my third formula here, which is delta x equals VIT plus 1/2 AT squared, I actually have everything there also. Okay, so it turns out you could use either formula. There's not always just one right way to solve things. You can use multiple ways. Now I'm going to use the one that already has delta x isolated on one side, so then I won't have to do any algebra to make my job a little bit easier, but you'd get the same answer either way. So my VI is 14. And my time is 3 seconds, and then times 1/2 negative 4.67 times 3 squared. So if I take 14 times 3, I get 42. And then if I do 0.5 times 4.67 times 3 squared, which is basically 9, I get negative 21.015. Let's go ahead and round that to 21.02. And then we're going to go ahead and subtract those, and then we have our final delta x value of 20.98. Okay, so when looking at an acceleration problem, there's definitely a little bit more going on, so you want to make sure you label your known variables, and then once you have 3 known variables, you're ready to go to solve for something, which is either going to be your solution directly or a number that is going to help you get one step closer to the solution. Either way, you're going to look at your formulas and find something that has your unknown variable and has the other 3 known variables matched up with it, so you can do the math and algebra to find your solution. All right, let's go ahead and move to question number 4, our first free fall problem. So we're going to go ahead and work out questions 4 and 5 together because they're both free fall problems. Now, anything that's in free fall is only under the influence of gravity and nothing else, as it's basically moving the air but not actually getting affected by the air resistance. In these cases, your acceleration is going to be negative 9.8 meters per second squared for anything that's in free fall, which means it could be going up, down, sideways, whatever the case, but because of the force of gravity, it's going to be slowing it down as it's rising and speeding it up as it's moving towards the Earth. And we have that free number of negative 9.8 meters per second squared. All right, let's start off with number 4, our purple problem. Our ball is thrown downward at 4 meters per second. And anything downwards, we're going to call that negative. So it's going to be important to make sure you include that sign. And then we have a time of 2.5 seconds. Okay, but remember, we got the free variable a equals negative 9.8 meters per second squared. Okay, so we're going to find the velocity after 2.5 seconds. So it looks like we have the starting velocity here, so we're going to have to find a final velocity after that 2.5 seconds. So I have 2 formulas with a VF in it. I have A equals VF minus VI over T, which actually does work out because I have A, VI, and T. And then if I were to try to use the other one with the VF squared, I don't have a delta X, so I can't really use that one. So I have acceleration equals VF minus my VI, so minus negative 4 all over 2.5. Now for this one, that negative is going to be very important, and you're subtracting the negative, which is basically adding it. And you're going to multiply both sides by 2.5 first, so that you don't have a fraction on the right side. And then after you do that, it looks like I got negative 24.5 equals VF, and we'll call that plus 4 because it was minus negative 4 to begin with. And then we just have to subtract 4 from both sides, and then we're done. We have negative 28.5 meters per second. So basically what's happening is for every second the ball is falling, you're subtracting 9.8 meters per second, so basically giving it an additional 9.8 meters per second of velocity per second in the downward direction. That's what the negative is for. So it started at negative 4, and then it got 2 of those negative 9.8s for 2 of the seconds, and then half of that negative 9.8 for that extra half for that 2.5 seconds total. So we should end up with a bigger negative number, kind of like the 28.5 meters per second. All right, now for our second calculation, the orange one. Now, the ball is tossed up at 10. What is its maximum height? So it seems like there's very little information there, but let's actually clear a little room before we solve this one. Okay, it's tossed up at 10. Now, the thing about these free fall problems is that it seems like you have very little information, so it's going to seem like you don't have enough to solve the problem, so you have to think about some concepts, like we know that we get the free negative 9.8 meters per second squared for anything that's in free fall, and then because it's going to the maximum height at the very peak of its flight, it has an instantaneous velocity of 0, because if something slows down until it eventually changes direction, it does have to tap 0 meters per second for an instant, which is just a non-measurable amount of time, but it does have to hit 0 meters per second as it goes from positive to negative. Okay, and the VI is this 10 from over here. Okay, so that one variable now turned into 3 known variables, and then we're looking for the maximum height. Okay, instead of calling it delta x, we're going to call it delta y because it's the change in the y, the vertical position, not the change in the x, the horizontal position. Now it looks like if I'm looking at my formulas, I'm looking at the ones with the delta x in them because they're basically the same as the delta y, and it looks like I have to use my VF squared one because my other one, the VIT plus 1/2 AT squared one, has times and I don't have time. So I'm going to have VF squared equals VI squared plus 2 times negative 9.8 times delta y. Our 10 squared is going to come out to 100. So let's go ahead and move that one first and then subtract 100 from both sides, which basically is going to make this side that's just 0, negative 100. We can multiply these two, which is going to give us negative 19.6 times delta y. And now we're almost done. One more step, we're going to divide both sides by 19.6, and then our signs are going to naturally work out nicely for us. We have two negatives divided by each other to get a positive delta y, and then that delta y comes out to 5.10 meters. Okay, and that naturally came out positive because the object is rising and its height is directed in the positive direction. All right, now when you work out these free fall problems, it's important to make sure everything down is negative and everything is up is positive. You have that free negative 9.8 meters per second squared for anything that's in free fall motion, and there are some key numbers to remember, like the VF of 0 at the very peak of its flight. Some other important ones are that if something goes up but then travels back down to the same height, then the VI is equal to the negative version of that number when it comes back down to the same level. So if it gets tossed up at 10, it's going to come back down and hit the ground at negative 10. If it gets tossed up at 20, it comes back down to the ground and is negative 20, and then the time it rises is the same as the time it falls, assuming that it returns back to the same height. Okay, so those are some concepts that you might need to use and kind of help you find some more variables in certain cases. All right, now moving on to 6 and 7, our last two problems that are 2D acceleration problems that are projectile problems. So for our first projectile problem, we have a soccer ball that's kicked at an angle of 30 degrees with a velocity of 10 meters per second. How long is in the air for, and what is its range? So we have something that is 30 degrees above the ground. It has a velocity of 10 meters per second, and then it's going to go through this arcing motion here. We want to find the time in the air, and we want to find the range. The range is the delta x, the change in its horizontal position. For these kinds of problems, 2D projectile problems, the first step you want to do is for sure split everything up into a horizontal x column and a vertical y column. Now the reason why you do that is because everything in the x column is things that represent the horizontal motion of the projectile, which is moving at a constant velocity. So we're going to use this constant velocity formula for anything in the x column, because Fg, the force of gravity, pulls down, it does not pull side to side. So we have constant motion in our x column. In our y column, we know that's affected by the force of gravity because it's pulling down. So anything that's moving up is slowing down, and everything that's moving down is speeding up. So we're going to use our 3 green acceleration formulas if we have anything on the right side. All right. Now with that being said, also one of your typical steps for these problems is taking this 10 meters per second and then breaking it up into x and y components, because that 10 doesn't fit into either column because it's on an angle. So we want to make a little triangle off to the side here, and our hypotenuse is the 10 meters per second, and then we have a velocity in the y direction and a velocity in the x direction. So for our y, velocity, we're going to use the sine of 30 degrees, so we get the opposite end along with that hypotenuse, and then multiply both sides by 10, and then we have a vertical velocity of 5 meters per second. And then in the horizontal direction, we're going to use cosine because that's going to give us the adjacent side, and that is Vx over the hypotenuse, and 10 times cosine of 30 is going to give us a Vx of 8.66 meters per second. All right, now when we slide that into our x and y column, obviously the Vx is going to go over here, 8.66, that is our horizontal velocity. We only need to enter one velocity there because it's a constant velocity. And then for this one, we're going to call the Vy our Vi because it's our initial velocity. Okay, now remember, if you remember the free fall problem from earlier, I said if something goes up at 5 meters per second, it's going to come back down to the ground at the same number, different sign. So our final velocity is negative 5 meters per second, and we know our acceleration is negative 9.8 meters per second squared. Meters per second squared as usual. All right, so if you're taking a look at the left side and the right side, clearly we do not have much on the left side, so we're going to use our formulas on the right side, which are the 3 green acceleration formulas, and we want to solve for time and delta x. So we can solve for time in either column because time is not a vector, it doesn't have a direction, so you could find time in either column, but we're going to use the y column because we don't have enough in the x column. With that being said, we have negative 9.8 equals Vf minus Vi over t, which is our first acceleration formula. And then we're basically going to cross multiply these, and we get negative 10 over negative 9.8, which gives us positive 1.02 seconds. All right, now that we got our time is our only variable that can fit into either column, so I can go ahead and take that time and slide it in right over here. And then now I have everything I need to find my delta x because the formula is delta x over t equals v. So let's go ahead and set that one up. I'll set it up over here. So we have delta x over t, 1.02, equals our v. And then if we multiply both sides by 1.02, we got our answer, and our delta x then comes out to 8.83 meters. All right, so let's recap that one because there's a lot going on there. Now, when you have a 2D projectile problem, definitely set up your x and y column. Anything that's horizontal, put in your x column. Anything that's vertical, you're going to put it in your y column. We do that because they're two different kinds of motion. Therefore, you will use two different types of formulas. Just one kind of formula for the x side, which is the constant velocity one, and the 3 acceleration formulas for the y side. On the y side, you typically have a little bit more, not always, but we have your negative 9.8, and then we want to make sure we take our initial 10 meters per second and always use a little trig as we did with our triangle to find some y components and some x components. That way we can get the problem started with a couple extra numbers, and then depending on what they're asking you, kind of work your way from there and then do a little bit of algebra using some of our kinematic formulas. All right, let's get to our very last one, a time and range for an elevated projectile launch. Now for this problem, I used the same angle and velocity as the previous one to make things a little bit more simple. So the ball is launched at a 30-degree angle, and that was at 10 meters per second like the previous one, but it's off a 3-meter platform. That actually changes the complexity of the problem quite a bit. So it's a 3-meter platform, and it's fired at 30 degrees and 10 meters per second. All right, so same as before, we're going to go ahead and use our x and y column. And what we're going to do is we already did this in the previous problem where we took the sine of 30 times 10, and that gave us our velocity in the y direction of 5 meters per second. Then we took the cosine of 30 times 10, and that gave us the x component of 8.66 meters per second. Okay, if you skipped over the video to this problem, then go back to the previous one because I'll talk about the setup in a lot more detail. So go back to problem number 6 and watch that one in detail, and then come back to this one. All right, now in the previous one we said our VI is 5 and that our VF is -5, but that's only if it returns to the same height. Now this one is shooting off a 3-meter platform, so we don't know the VF, but we know the 3-meter drop-off is going to give us a delta y of -3 meters because it's displaced 3 meters below its original position, and we have our acceleration of -9.8 meters per second squared as usual. All right, now if we want to find our time and then eventually our delta x or our range, it's going to be a bit trickier here. So I want to use VI, delta y, and A to find a time. And the only formula I can use is this one right over here. The other ones require a VF, and I don't have a VF, unfortunately. So here's what I'm going to do. My delta, well, it says delta x here, but I'm going vertical, so my delta y is -3. My VI is 5. T is unknown. 1/2 -9.8, and then t squared. Okay, so if we set this equal to 0, we do 1/2 times -9.8, then 1/2 times -9.8 is -4.9 times that t squared. Okay, that takes care of this one. And then plus 5t, which is this one over here. And then if you add 3 to both sides, it just brings a 3 over here. All right, we can solve this a couple different ways. We could either use the quadratic formula, and that will give us a positive and negative t value. We could graph it in our calculator and find the intersection points of where it crosses the x-axis. Either way works. Okay, when you do that, you will get a t value of 1.44 seconds and -0.42 seconds. Okay, and then the dead giveaway is that you're just going to take your positive number because we don't have negative times. And that's our answer, 1.44 seconds. Okay, now from there, we can go ahead and find our delta x like we did previously. We can take our time, and remember, the time is the only thing that can slide from side to side because it's not a vector, it does not have a direction. So we can say delta x over t equals 8.66, multiply both sides by 1.44, and then I have a delta x of 12.47 meters. Okay, so again, the main thing you want to do with projectiles is number 1, break up your velocity into its x and y components using cosine for the x component and a sine for the y component. After that, organize everything in your x and y column. Now, depending on the problem, if it's something that returns back to its original height, your VI and your VF are going to be the same number, different signs. If you're going to the peak of its flight, you could use a VF of 0 because it has an instantaneous velocity of 0, and you can always definitely use your -9.8 meters per second squared on your y side. Okay, other than that, each situation is going to vary a bit, but you want to pull at least 3 numbers on the right side or 2 numbers on the left side to do some solving, and then hopefully you'll find your solution from there. So I hope that was helpful to you in building up your skills with problem solving kinematic problems. Thank you for watching and listening.